ಕರ್ನಾಟಕ LMSಗೆ ಸುಸ್ವಾಗತ. Myself Suguna HG, Assistant Professor, Government First Grade College, Chintamani. In this video, I am presenting you standard problems on groups. First problem, show that the cube roots of unity form an abelian group with respect to multiplication. So here we have to show that the set cube roots of unity G is equal to 1 omega omega square forms an abelian group. So to show that, write the composition table. The composition table is shown below. See, with respect to multiplication dot and the elements of G are 1 omega omega square. So in the first row 1 omega omega square I have taken, and similarly the first column 1 omega omega square. Now let me fill the table by using the binary operation multiplication. 1 into 1 is equal to 1, 1 into omega is equal to omega, 1 into omega square is equal to omega. This column, that is the leading element, is 1. So 1 into 1 is 1, 1 into omega is equal to omega, 1 into omega square is equal to omega square. Now let us fill the second column, that is omega into omega, which is equal to omega square. Omega into omega is equal to omega square, and omega into omega square, omega into omega is equal to omega square, omega into omega square is equal to omega cube. In the cube roots of unity, omega cube is represented by 1, and next omega square into omega is also again omega cube. So we have filled this column also. Now the last element is omega square into omega square, which is equal to omega to the power of 4. Omega to the power of 4 is omega cube into omega. So omega cube is equal to 1. Therefore omega to the power of 4 is represented as omega. Now see, we have filled the columns and rows of the table. So they are 1 omega omega square, omega omega square 1, omega square 1 omega. See, all the entries of the composition table belongs to the set G. Since each entry in the composition table is an element of G, so G is closed under multiplication composition. Next, from the table it is understood that the associative law also holds good. All the elements of G is being complex numbers, and the multiplication of complex numbers being associative, it follows that multiplication is associative in G. Now see, in this table, suppose if you take 3 elements, 1 omega omega square, so 1 into omega is omega, then omega into omega square is omega cube, that is also equal to 1. And see, if you multiply in the different order, omega square into omega is equal to omega cube, that is equal to 1. Again 1 into omega is equal to omega. So the associative law is satisfied. Next, the existence of identity. It is clear from the composition table that 1 into 1 is equal to 1, 1 into omega is equal to omega, 1 into omega square is equal to omega square, and even omega square into 1 is equal to omega square. See, when you multiply with the 1, every element, then the product remains the same. So the element 1 belongs to G, is the multiplicative identity in G. See, from this table, 1 into 1 is 1, 1 into omega is equal to omega, 1 into omega square is equal to omega square. And similarly, see, the first row and first column of the composition table are identical. So which implies that the identity element is the leading element of corresponding these rows and columns. The leading element is 1. Therefore 1 is the identity element. Existence of inverse. From the table, 1 into 1 is equal to 1, omega square into omega is equal to 1, omega square into omega is equal to 1, and omega into omega square is equal to 1. So inverse of 1 is 1. inverse of omega is equal to omega square. Omega square whole inverse is equal to omega. So by this one, it implies that every non-zero element of this group has multiplicative inverse. Therefore, the inverse exists. Commutative law. Composition table is symmetrical about the principal diagonal. Therefore, commutative law holds good. Hence, G dot is a finite abelian group of order 3. So, this is the principal diagonal, and this table is symmetrical about the principal diagonal. That means above the principal diagonal the elements are 1, omega square, omega square. Similarly, below the diagonal we have 1, omega square and omega square. So, it is symmetrical about the principal diagonal. Therefore, the commutative law holds good. Hence, the given group is a abelian group. So, the commutative law holds good. Hence, G dot is a finite abelian group. See, in order to show that G dot is an abelian group, we have to prove the closure law, associative law, existence of identity, existence of inverse, and commutative law. If all these 5 laws holds good, then the given set is a finite abelian group. And its order is 3 because the set G contains 3 elements. Next problem. Show that G is equal to matrix 1 0 0 1 comma matrix minus 1 1 minus 1 0 comma matrix 0 minus 1 1 minus 1 is also an abelian group with respect to multiplication. Let us consider I is equal to 1 0 0 1 and A is equal to minus 1 1 minus 1 0, B is equal to 0 minus 1 1 minus 1. Multiply this with an identity matrix, that is I into A is equal to 1 0 0 1, this is I with respect to 2 by 2 matrices, and A, that is minus 1 1 minus 1 0. Now when you multiply with the I, you get the same element, that is the first row into first column, that is minus 1 plus 0, so minus 1. Then first row into second column, 1 into 1 is 1, 0 into 0 is 0, so 1. Second row into first column, that is minus 1. Second row into second column, 0. So this matrix is nothing but A. See, when you multiply A with I, the resulting matrix is A itself. Next, let us multiply with the B also, that is I into B. I into B is equal to 1 0 0 1 0 minus 1 1 minus 1 0. Then the product of these two matrices is 0 minus 1 1 minus 1, which is nothing but B itself. So what does it implies? AI is equal to A and BI is equal to B. Means the product of the identity matrix with the given matrix is the same, that is the given matrix itself. AI is equal to A and BI is equal to B. Now let us find out AA. AA is equal to minus 1 1 minus 1 0 and minus 1 1 minus 1 0. So when you multiply these two, first row into first column, first row into second column is the first row, and second row into first column and second row into second column is the second row, that is 0 minus 1 1 minus 1, which is nothing but the matrix B. The matrix B. So A into A is equal to B, and similarly when you multiply B, you will get B into B is equal to A. AB is equal to minus 1 1 1 minus 1 0 0 minus 1 1 minus 1, which is equal to 1 0 0 1, which is nothing but the identity matrix. When you multiply AB, we are getting I identity matrix. Similarly, BA also we get identity matrix. So AB is equal to I, BA is equal to I, BB is equal to A, AA is equal to B, AI is equal to A, BI is equal to B. So by using these results, let us have the composition table. See, in the composition table, I have taken with respect to multiplication I, A, B, I, A, B. Now let us fill the composition table. First I into I. I into I means identity matrix into identity matrix. It is I itself. I into A. What is I into A? It is A itself. Then I into B. It is B itself. And similarly A into I is equal to A. B into I is equal to B. Now A into A. A into A is equal to B. And A into B is equal to I. B into A is equal to I. IAB, first row is IAB, first column is IAB, and BII, and B into B is A. So now we have filled this table completely. All the elements of this table are belonging to the set G. Therefore, the closure law is satisfied. See, G contains IAB, so all the entries are belonging to that. Then associative law also holds good in matrix multiplication, because I into AB, let us take I into AB is I into I, because AB is equal to I, and which is equal to I itself. Now I into A, we are interchanging the brackets. I into A into B is equal to I into A is A itself, and A into B is equal to I. Now you see, I of AB is equal to I, IA of AB is also equal to I. Therefore, the associative law is satisfied. Even from the table also we can verify that I into A, B, let us take A into B is equal to I into I is equal to I. Then identity element, see the first row and first column of the composition table are identical. Therefore, the identity element is I. Identity exists and which is equal to I. Now, let us go to the inverse property. Inverse of IAB are respectively IBA. See, inverse of I. Wherever you have I in the composition table, corresponding to that, let us take the column and row leading elements. So, this is I into I is equal to I. Therefore, inverse of I is I. Then in the second row we have I here. So inverse of A is B, and in the third row I is in this place. So in third row the I is here. So B inverse is equal to A. The inverses of IAB are respectively I, B, A, and from the table it is clear that A into B is equal to I, and B into A is also equal to I. Therefore, the commutative law holds good. Now, see all the 5 axioms: closure law, associative law, identity, and inverse exists, and commutative law also holds good. Therefore, G is an abelian group under matrix multiplication. Third problem. Show that the set of all complex numbers Z with modulus of Z is equal to 1 is a group with respect to multiplication. Now let us consider the set G is equal to Z such that Z belongs to complex numbers and modulus of Z is equal to 1. Take 2 arbitrary elements Z1 and Z2 belongs to G, then modulus of Z1 is also equal to 1, because in the set it is defined as the modulus of Z is equal to 1. Therefore, modulus of Z1 is 1, modulus of Z2 is also equal to 1. Now, modulus of Z1 into Z2 let us consider, which is nothing but modulus of Z1 into modulus of Z2. Modulus of Z1 is 1, modulus of Z2 is 1. So, 1 into 1 is equal to 1. So, this implies that Z1 into Z2 belongs to G, because the modulus of Z is equal to 1 is present in G. Hence, Z1 into Z2, the product is equal to 1, which also belongs to the group G. Thus, Z1, Z2 belongs to G implies that Z1 into Z2 belongs to G. Therefore, the multiplication is binary operation in G and it is closed. Okay. Since C Z1, Z2 belongs to G we have taken, and we proved that the product Z1 into Z2 belongs to G, hence it is closed with respect to multiplication. Second, the associative property holds good for multiplication of complex numbers. See, we know that the associative property is also holds good in multiplication of complex numbers. Therefore, associative law also satisfied. Now coming to the identity element, since 1 plus I0 is also a complex number, when you take the modulus of that, that is equal to 1. Therefore, which implies that 1 plus I into 0 belongs to G, hence 1 is the identity element. Let us consider Z belongs to the set G, then modulus of Z is equal to 1. Therefore, 1 by Z modulus is equal to 1 by modulus Z, which is equal to 1 by 1, that is nothing but 1. Hence 1 by Z belongs to G, and also Z into 1 by Z is equal to 1 by Z into Z. See, the product of these two, Z and Z get cancels. So it is equal to 1. Therefore, every element of G has its own multiplicative inverse. Hence, G dot is a group. Thank you.